Alright, so today we're going to do section 14.6, and we're going to be looking at polar graphs. So we want to be able to graph polar equations, test for symmetry and zeros, and recognize, understand, and graph special polar graphs. But we do want to note, semester's almost over! Woo! So we're excited about that. Moving on. So now take out your graphing polar intro sheet, and we're going to do some of those graphs. So if r equals 5, I want you to graph this equation either by continuing to keep it in polar or convert it to rectangular, but you should be able to understand what this should look like without converting it to rectangular. If you don't, though, go ahead and do that, and then it should hopefully make sense. I'm going to stop rambling now, pause the video, graph this, unpause it when you're ready to check your work. Okay, so hopefully you recognize this is just a circle with radius 5 and the center at the origin. So here in green you can see that this is what it would look like if we converted it to rectangular, where I can see that it's a circle of radius 5 and a circle at an origin. But if I just look at the equation r equals 5, what is that telling me? That's telling me for any angle theta, r is 5, which means that I have a circle with radius 5. Alright, let's go on to the next one. If theta equals pi 6. So I want you to pause the video, try to graph this, unpause when you're ready to check your work. Alright, so for this one, again, you can convert to rectangular. You could see that it's a line with a slope of root 3 over 3x. I'm sorry, the slope is root 3 over 3, y-intercept is 0. Or you can recognize, what does it mean for theta equals pi 6? That means for any value of r, theta is always pi 6. So it's just tracing the line pi 6. So this is just a line. Next, r equals 3 secant of theta. So I want you to graph this. Pause the video, unpause when you're ready to check your graph. Okay, so here we should just get a vertical line at x equals 3. We can again see that if we convert this to rectangular. Or I get that if I start plotting points. So if I pick values for theta, so I chose 0, pi thirds, pi, 2 pi thirds, 4 pi thirds, and I see the r values are 3, 6, negative 3, negative 6, negative 6, and so on. And then if I start to plot those points and connect the dots, it's just going to be a line. It's going back and forth, up and down the line. Next one, try and graph r equals 4 sine theta. So pause the video, and pause when you're ready to check your work. Okay, so here our picture is going to look something like this. What it turns out, and we'll find this later on toward the end of this lesson, is that this is actually a circle of radius 2, but the center now is at the point 0, 2. But again, for graphing this by hand, I don't expect you to necessarily know that right now. So I plugged in these values of theta and plugged in these, which gave me these values of r. I chose these values of theta because I know those are going to be nice for sine. Obviously, it doesn't do a great job of getting the actual picture in this case. Another question you might ask: how do I know to stop at pi? Well, I don't, but I can picture in my head, or kind of do the math in my head. Well, what if I plugged in 7 pi 6, which would have been the next value that I would try? So 7 pi 6 would be this line right here. What would the value be for 7 pi 6? It would have been negative 2. So that would jump over to this point again. And if I did, for instance, 3 pi halves, then I would end up with negative 4. So that would be back up here. So I can see that if I started to, or if I continued to go on with angles up until 2 pi, it would just repeat this same circle. So that's why I stopped at pi for this example. Next one, what if it's r equals 5 cosine of theta now? So pause the video, graph this, unpause when you're ready to check your work. Here our graph is going to be a circle again. Now it's going to have a center at the point 2.5 comma 0, and it's going to have a radius of 2.5. Again, I don't expect you to necessarily know that right now. We'll understand that at the end of the lesson today. But hopefully you should get a picture that looks something like this. same reason I knew to stop at pi this time for what I did last time is if I continue on with, for example, my next one would have been 4 pi thirds. Then that's going to be at, 4 pi thirds would be here, it'd be at negative 5 halves, so that would jump back up to this point, and so on. One thing that can also help you with these is think about what would the graph of this function look like, and that can help you understand when you can stop plugging in points, because whenever the cycle is going to start to repeat. Alright, what about r equals theta? Pause the video, graph this, unpause when you're ready to check your work. I'll give you a hint, your graph will not be perfectly accurate, but you can do a pretty good job. Pause the video. Okay, so here your graph should look something like this. It should be a spiral. It's going to continue to grow. So actually my arrow here, it's probably doing more like this. But it's going to continue to spiral around, and that is because for r equaling theta, that means when theta is 0, r is 0. When theta is pi fourths, r is pi fourths. When theta is pi halves, r is pi halves. So as theta continues to grow, or as you continue to go around the circle, r is going to continue to expand. Okay, now let's talk about symmetry. Okay, so we have 3 types of symmetry that we're going to look at. One is symmetry with respect to theta equals pi halves, so the vertical axis. How do we test for this type of symmetry? We want to replace r comma theta. This would be, let me start over a little bit. This would be the same as saying y-axis symmetry, but because that's the line that theta equals pi halves, so the test is very similar. So we're going to replace r theta with r pi minus theta, or negative r negative theta. And what we're doing is we're looking to see, does that become the same as the original? So for example, something that is symmetrical to theta equals pi halves would be the equation r equals 4 sine theta. How do I justify that? Well, let's replace it with negative r negative theta. So negative r equals 4 sine of negative theta, but I know sine of negative theta is negative 4 sine theta from my even odd identity, and now if I divide both sides by negative 1, I end up with r equals 4 sine theta. So since if I replace r with negative r and theta with negative theta, this went back to the same as the original equation, I know it is symmetrical to the line theta equals pi halves. The next symmetry we're going to talk about is the polar axis. This is the same as saying the x-axis. So here we are going to replace r theta with r negative theta, or negative r pi minus theta. Obviously, it's one of those is easier than the other. So our example here is what we did, the circle over the x-axis, so r equals 5 cosine theta. So now we can say r equals 5 cosine negative theta, but from my even odd identity, this is the same as r equals 5 cosine theta. Therefore, since when I replaced theta with negative theta, it went back to the original equation, I know that this is symmetrical to the polar axis. Our last type of symmetry is symmetrical to the pole. So for the pole, replace r theta with r comma I plus theta or negative r theta. A basic example of this from what we've seen would be the line theta equals pi sixth. So here, since there is no r in the equation, if I replace it with negative r, it's still the same as the original equation because there is no r. Therefore, this is symmetrical to the pole. Alright, so those are our tests for symmetry. One thing you'll notice, so symmetry with respect, or symmetry for theta with respect to the line theta equals pi halves. A shortcut or something to look for that is if the equation is r equals something with respect to sine of theta, it's probably symmetrical to the line theta equals pi halves. If it's r equals something cosine theta, then it's probably symmetrical to the polar axis. Now these aren't hard and fast rules, but they're kind of shortcuts that can help you simplify symmetry. Maximums and zeros. So let's talk about those real quick. So for maximums, we can use calculus. So if we find our maximums, or I'm sorry, find the derivative, set it equal to 0, find our critical values, and then test those to see if they are maximums or minimums, we can use those to help us graph polar functions. Or we can convert them to rectangular. And what I mean by the rectangular graph, or convert them to rectangular, is actually graphing the trig function. So if you look at the graph of the trig function, it'll help you figure out where your graph should be 0 or have maximums and minimums. And then zeros, solve the equation. Or use the rectangular graph. And again, what I'm referring to is not necessarily convert it to rectangular, but for instance, if you have r equals 5 cosine theta, graph 5 cosine theta on your coordinate axis like we did back in first semester and look at where the zeros occur. Those zeros are going to be the same. Okay, next I want you to graph the polar equation y equals 2 plus 3 cosine theta. Pause the video, unpause when you're ready to check your work. I apologize real quick, I didn't mean to throw you off. That should have been r equals 2 plus 3 cosine theta. So now, try to graph that by hand. Sorry about that typo. Okay, so my graph should look like this. So the easiest way to do that here is I plotted theta values, or plugged in theta values through pi, where I knew that cosine would come out to be a somewhat nice number. I recognize that this is going to have polar axis symmetry, because if I plug in negative theta, that just goes away with cosine. So then I plotted these points, and then I plotted the symmetry of those points as well. I could have also done, and I didn't go through or finish the work, but I could have found the maximums and minimums by finding the critical values. So I know r prime is negative 3 sine theta, so 0, if I find the critical values, I set this equal to 0, and I know I'm going to have critical values at every interval of pi, every integer of pi. And then I could test to see where the maximums and minimums occur, but I can see from my graph by just plugging in points. Okay, so we're going to end this video here, but we do have a part 2. I know that's very exciting. So go on to part 2 now.